Hello everyone. This presentation is on joint controller and detector design against data injection attacks on actuators. The outline of the talk is as follows. I provide with a problem background in the introduction and formulate the problem, provide a design algorithm to solve the problem formulated before, um, and we discuss some numerical examples to see the efficiency of the algorithm, and finally provide some concluding remarks. To begin with, let's see the pictorial illustration of the Stuxnet attack, which happened in a nuclear power plant. The attack happened as follows: a malware entered through a USB stick into the control center of the nuclear power plant, traveled over the network, and after it reached the controller, it recorded the signals from the centrifuges as sensor measurements, played it back to the controller center as the replay attack, and then provided false actuator signals to the centrifuges. So in this way, the centrifuges of the nuclear power plant was ruined. There are also several other network attacks, such as in Destroyer, Black Energy, etc. So the aim of this talk is to design the controllers and detectors of a plant more optimally, such that the attacks on the controllers or on the plant can be easily detected. So to give a more clear understanding, we consider the following representation, where there is a process, which in the previous case was the nuclear power plant. There is an anomaly detector, which helps us to find if there is a data injection attack or any kinds of attack on the process, and a controller, which is an output feedback controller in this case. And in this particular paper, we consider that an attack or is being injected into the control signal. So when the signal is transmitted from the controller to the process, an adversary is trying to attack the control signal. So the setup is that the adversary injects false data into the control signal to increase the performance cost while staying undetected. So this is the objective of this is the setup, and the aim of the system operator is to design the controller and the anomaly detector to reduce the impact of the attack and improve detection. So given this setup, we consider a more mathematical formulation where for the process, we consider a linear time invariant system with output Y and virtual performance output YP. We consider a static output feedback controller OL and a Kalman filter based detector K. So here L and K are the controller and observer gains. As I said before, since there is an attack on the actuator signal, you can also see that if U is the control signal generated by the controller, the actual control signal applies U tilde, where U tilde is the actual control input U plus some attack. So there uh, for uh, for some preliminaries, let the system model from U to YP and YR be sigma R and sigma P. Those are just the system models. So previously we had the setup where the adversary is trying to inject false data to increase the performance cost. So given this mathematical formulation, we can change this setup into increasing the energy of the performance output while while the energy of the detection output is less than 1 for being undetected. This one is considered without a loss of generality here. So given this as a setup, this can be posed as an optimization problem where A is the attack signal and X0 is the initial condition of the system. So this is this is represented as output to output gain, which is formulated in the literature before. To solve this optimization problem and to take this forward, a critical assumption is that in this paper we assume that the adversary has perfect system knowledge, so that the matrices A, B, C, D are known to the adversary. So this is the problem background, or this is what the adversary tries to do. So given this problem background, what we can do in the problem formulation is that this is again the adversary's optimization problem. So the optimization problem is a function of the controller and the detector gains. So given this is an optimization problem with where the adversary is trying to maximize the impact on the system, we can use the controller and detector gain so as to minimize the impact caused by the adversary on the system. So that is the problem formulation here. And as you can see, we are interested in the infinite horizon problem here. So the attack vector lies in the extended L2 space. So in time domain, this means that the attack vector is infinitely long. To circumvent this problem, we consider we take into account the dissipative system theory. This dissipative system theory helps us to modify the problem from an infinite dimension of attack vector to a finite dimension matrix P. So to make this connection more clear, this is a proposition from dissipative system theory. So let's say that we have an infinite dimensional attack vector, which causes an infinite dimensional residue and an infinite dimensional performance. So this is equivalent to an existence problem where we solve for a finite dimensional matrix P, and ACL, V, CP, DP, CRTR are the system matrices. So from using this proposition, the previous optimization problem of the system designer can be translated into this non-convex design problem. Here, this problem is non-convex because of the bilinear terms, ACL, PACL. In this, ACL is a function of controller and detector, which are optimization variables of them in themselves, and also P is an optimization variable. So this is a bilinear problem. Before we see some tools to solve this bilinear problem, we see um, one limitation of this design problem in the next few slides. So the first result of this paper is that, let's say that we have a strictly proper system sigma R and a proper system sigma P. When under these conditions, the design problem becomes infeasible. Let's see why. So this is the LMI, which was the constraint in the previous optimization problem. As you can see here, one of the principal diagonal submatrix is BCL transpose PBCL plus DP transpose DP minus 0 is less than or equal to 0. So for dissipative system theory, we require that P to be positive semi-definite, and given that dp transpose dp is positive definite, we cannot find, or it is infeasible for a matrix P to exist satisfying this condition. Hence, the problem or the design problem becomes infeasible. A generalization of this theorem is stated as theorem 1 in the paper. So to solve this problem, what we do is that we also make the system sigma p strictly proper, or we delay the input to the system. So this is the approach. Under this approach, the optimization problem is modified into this optimization problem 8. It has to be noted that from the previous design problem that we considered here, ACL, VCL, CRD, CP are appropriately changed so as to include this delay. So as you can see here, although this solves one of the problems, this is still non-convex. So in the next few slides, we will see how to suboptimally solve this problem. So this is the constraint. First, So given that we require BCL transpose PBCL is less than or equal to 0, we can just enforce PBCL to be exactly equal to 0 since P is positive semi-definite. So this is the first foundation. And the second foundation is that given this constraint, we can apply since this is a bilinear term, we can apply the Schur complement to this term. But the problem here is that we only, from a dissipative system theory perspective, we require P to be positive semi-definite, and for Schur complement, we require P to be positive definite. And to and to uh, and to overcome this problem, what we do is that we split matrices into blocks where so the ACL block is divided into submatrices, and the first submatrix, A tilde, is the only matrix which is dependent on K and L. And correspondingly, we also split the matrices P, CP, and CR. So the Schur complement, which I said in the previous slide, is only applied in regards to Px instead of the whole matrix P. So applying these foundations to the optimization problem of the system operator, we get this modified optimization problem 9. So why do all these to get to this optimization problem is that since in this optimization problem, we can apply the technique of alternating minimization. Um, the foundation of alternating minimization is given in the following slides. So we take the optimization problem, we optimize it with respect to one of the parameters, and then update it, and then optimize again optimize the optimization problem with respect to the other parameter. So this is the technique used in this paper to obtain a suboptimal controller and detector. Um, so given this optimization problem, we now look into numerical examples. So we consider a system with A, B, C, Cj, Dj given in this as represented in this slide, and with this system matrices, we apply a control. We apply an attack signal of this form, and we obtain the singular values of the system for varying frequencies omega. We can see that uh, insignificantly the gain of the detector gain is improved quite a bit, and the effect of the attack signal on the performance output is reduced significantly. To further analyze these results, we can see the individual improvement in particular frequency regions as follows. In the low frequency region, we can see clearly that the detection is improved. The gain of the detector is very much improved compared to the classical H minus metric, and the impact of the attack signal on the performance output is reduced significantly compared to the classical H infinity metric. This is at the low frequency region. In the mid frequency region, we can see that the performance deteriorates, but the upside of this method is that the detection is improved significantly at the at the sacrifice of performance. So this can be said to be um, a good trade-off. And the high frequency, it can be seen that the detection is very poor, but the detection is very poor only when the performance is also very poor, in a sense that the detection is improved in this design only when the influence of the attack signal on the performance output is very high. So this is the result of this paper. So in conclusion, we have considered attacks which focus on injecting data into the actuators while remaining undetected. And we have considered output to output gain as a design metric discussing its limitations and leveraging it. We have proposed a joint controller and detector design based on alternating minimization, and we have also provided some numerical examples to compare the effectiveness of the proposed approach. Um, these are the references which was used in this paper. Thank you very much for your time.